So, we will now present the 5 MERLIN case scenarios as example of the benefits that MERLIN can bring. And I will call to the floor the first 2 speakers from scenario 1, Eric Prétet and Olivier Langlois. Okay. I'll briefly introduce both of them. So, you will see, after my short presentation of the speakers, you will see a video clip presenting the problem and the solution side. And the problem in scenario 1, which is energy management solutions to improve capacity of the SNCF high-speed line Paris-Lyon in France, will be presented by Eric Prétet, who is a graduate engineer from the École Centrale de Paris. He is project leader in the innovation department of SNCF Reseau. And within the scenario 1 of MERLIN, Eric was in charge of defining the needs of the French railways in order to increase the capacity of this high-speed line number 1. The solutions will be presented by Olivier Langlois, who is an electrical engineer and PhD holder, working on railway energy management topics for Alstom Transport in France. Am I correct, Olivier? Okay. In the MERLIN project, Olivier was involved in the development of the reference architecture of Work Package 2, some simulations, and also in technical recommendations, part of Work Package 7, but especially in the smart grids of Work Package 4. So we'll now see a short video clip. Thank you.
French Railways wish to increase the capacity of high-speed line 1, which is between Paris and Lyon. And one of the difficulties is that the public power system is weak between the crossing of the Morvanville, which are roughly halfway between Paris and Lyon, and that it's not reasonable to build a new substation where the increase of capacity will need. We wish to increase the capacity of the line from 13 trains per hour till 16 trains per hour. This is to say that an increase of roughly 3 trains per hour. We hope that better management of the energy available will allow this increase of capacity. Better management is first to use substation with a storage system. The substation will store the energy during the night and reuse the energy stored during peak hours. And the second track is that better use of the energy available by monitoring of the speed of the train that will smooth the use of energy. So this is the problem that we address to MERLIN.
The first solution is a software solution which aims to shift a complete timetable of trains in one direction in order to avoid accelerating of different trains at the same time. This aims at reducing power peaks and power reduction at substation levels. The second solution is also a traffic management solution using an ATS, automatic train supervision system, which solves conflicts between trains, for example, avoiding braking, stopping and accelerating. There is significant benefits when we avoid a train to stop. The third solution is a hardware solution with the modification of existing substation, adding alternative energy sources like renewables or adding energy storage system. For example, when we store energy during the night, we can re-inject it into the railway power system in order to reduce power consumption during rush hours. Finally, the three solutions can be combined in order to minimize the energy consumption and reduce power peaks, and then increasing the line capacity.
Hello. So I will present more precisely the first scenario. Here's the line map between Paris and Lyon. It's not scale, but we can see here the area where the Morvans Hill. In reality, it's bigger than this, but as I said, it's not a scale line map. More in detail, this line is the first high-speed line in operation. It's connecting Paris and Lyon, which are separated by more than 400 kilometers. The length of the high-speed line by itself is a little bit less than 400. The commercial speed is up to 300 kilometers. It's a double-track line with bi-directional tracks and, of course, because the speed is high, cab signaling system. On the energy and electricity point of view, it's 25 kilovolt, 50 hertz AC. And the railway undertaking company, SNCF, buys electricity directly from energy providers, and electricity is routed by RTE, which is the French public power network. Power is provided to the line by 8 substations, with 225 kilovolt power supply, and 1 substation with 400 kilovolt input power. That makes a total of 9 substations, which are listed here. So we have, we can see the list of the substations. I just want to point out again the kilometers, and we can see more precisely the length between the 2 substations Sarin Commune, which are in the Morvans Hill. To go more precisely in the work made with MERLIN, the public power system is weak at the crossing of the Morvans Hill, which is halfway between Paris and Lyon, and SNCF wished to increase line capacity to high-speed line from 13 trains per hour up to 16 trains per hour and per way, roughly. Well, I said roughly because maybe you could notice that 13 plus 3 is exactly 16, but I say roughly because it's not exactly 13, because there are trains we are not crossing the Morvans Hills. Maybe we can see them on the diagram here. There are trains leaving the high-speed line to go to Dijon and Switzerland, and so that's the reason I say roughly, because it's not exactly 13, it's not exactly 16, it's not exactly 3. But I think it's simpler to say 13, 16, and 3. So to increase this line capacity, there are several issues, and electricity is one of the issues. The solution, the tracks that we wanted to work with MERLIN during this project, they were those tracks, and the first one, it's to monitor safely the spin of the train to smooth the energy used, and the second track is to use energy storage system at the 2 critical substations, which are Sarre and Commune. This energy storage system would boost the substation during peak hours. And now I leave the floor to Olivier, who will present how we worked on MERLIN.
Okay, good morning, everybody. So Now I will present the different solutions about this scenario. So as you saw the video, so you know everything about the solutions. But I will speak a little bit about it now. So the three solutions studied within this scenario can be divided in two different groups. The first group is software solutions. So at software level, we can, it's more traffic management solutions, like timetable shifting and traffic regulation with the automatic train supervision system to avoid brakings, accelerating, etc. And the second category of solution is hardware solutions, introducing hybrid substations, for example, combining alternative sources like renewables with traditional substations. So the solution number one is hardware software solution. So it's more traffic management solution, for example, with train shifting. If we shift several trains in the timetable from one direction to the other direction, we can separate and more or less avoid braking some trains at the same time and accelerating at the same time, so it reduces power peaks on the electrical system. And the other solution that was studied is more eco-driving solution to work on the speed profile of the trains in order to minimize the energy consumption of all the trains in the timetable. So it's really designed offline, so not in real time with real traffic, in order to get a more optimized in terms of energy and power peaks timetable. The solution, for the first solution, we can expect some percentage of reduction of powers and energy, but the solution number two is more a real-time solution for traffic management as well. So the idea is to use the automatic train supervision system to solve conflicts that can appear in the real situation, in real life of the trains. So I will detail a bit more this solution with a real example based on the real timetable on 2 years ago. I think it was on a Friday with rush in peak hours. This conflict I will present is based on two different trains that coming from the south to the north, and the first train need to stop in Macon station in order to let another train go to Paris. So we can see it on the timetable, so in a time and space diagram. Here. Okay. So in the full timetable here, so here are the distances. So here it is Lyon and Paris at the top of the image, and the time is from left to right. So if we look at the conflict exactly, so we can see that the dark blue train here is going from Lyon, and it stops in Macon station in order to let another train come into the high-speed line. It comes from another line. There is a junction here, and the train in dark is stopping to let the light blue train go up to Paris. So if we look at the speed profiles of the trains, so here it is the trains that needs to stop in Mâcon. Sorry. Okay. So we can see the speed profile of the train. So it accelerates on the high-speed line with the maximum top speed of 300 kilometers per hour. And here we can see that it brakes hardly to stop in Mâcon station. So he waits 8 minutes, and after he re-accelerates in order to reach commercial speed, normal speed. So, as we can expect, this is not an optimal speed profile in terms of energy consumption. So, the proposition made from the ATS is to anticipate the conflict, as we know that the train needs to stop in advance. So the idea is to make the train costing 40 kilometers in advance before Mâcon station. So the train as well is helped by a negative slope, so it allows the train to maintain quite reasonable speed. And then the train does not need to stop and just need to accelerate a little bit after the train the other train reaches the high-speed line. So in this case, we can expect a reduction of energy consumption of 10% on the whole travel of the train between Lyon and Paris. So here it's the solution illustrated by the timetable. So we can see. Sorry. Okay. We can see here that the blue train has reduced speed, so it makes more time to reach Mâcon, and when you reach Mâcon, the light blue train is already on the high-speed line, so it can go further up to Paris, and there is no need to stop. The third solution is a hardware solution. So now it's not only software. We need to add some hardware materials like energy storage system or other sources, for example. So in our case, in our scenario one, the traffic solutions are not enough to reach the capacity of 16 trains per hour. So we need to add alternative sources to conventional substations or add a new substation, but that's not the aim of an innovative solution. So the principle is illustrated here. So we can see here a conventional power supply system for the railway. So with a transformer connected from the national grid, feeding the AC 25 kV system in our case. So the idea is to add a kind of smart grid system. So it's more a microgrid located close to the substation. The idea is to connect several sources, one or several sources, energy, to feed the railway system. So, for example, it can be wind turbines here, or PVs, or hydraulic power plants, or storage systems, All these sources are parts of the distributed energy sources of the architectures presented before by Valeria. So in our case of the scenario 1, we finally choose to put storage systems in order to feed the power and to be recharged and to feed the railway systems during rush hours. So, as conclusions for this scenario, so I would like to emphasize that it's very important to combine these three solutions to maximize energy benefits. And it's follow a logical approach. The first solution, 1 and 2, which are software solutions, are less costly than adding hardware systems. So it's natural to firstly optimize the timetable offline. Then, in case of conflicts, we have to improve the management of the traffic in order to solve conflicts in a more energy efficient way. So this is solution number 2. And if it's not enough to provide enough power to the trains, we can add alternative sources in order to feed the railway system. So it's very important to have in mind this kind of methodology in order to not have too much investment than necessary. Okay, so thank you for your attention.
Thank you very much, Eric and Olivier. We'll save some time after the presentation of the 5 scenarios for a question and answer session. I will now call to the floor Niklas Biedermann, who will present the scenario 2, optimization of power flow in 15 kV, 16.7 Hertz system in Sweden. Sorry, it's very technical. I'm non-technical. Niklas holds a master's degree in electrotechnical engineering. He works as power system engineer for Trafikverket, the Swedish Transport Administration, where he is involved in power system design and planning. Within MERLIN, Niklas was in charge of specifying the needs of Trafikverket to set up the MERLIN scenario 2 that he will present after the little video clip that is going to be launched. Thank you.
We are looking at 2 different problems in MERLIN. The first one is about minimizing losses in the rail power grid. We are examining a line between Malmö and Alvesta in southern Sweden. It's a double-track line with quite heavy traffic, daytime mainly passenger traffic, and during night freight traffic. There are 3 converter stations on the line, and we are seeing that these converter stations not just are feeding the trains near the station, but also over longer distances. And this causes losses, and energy costs money. So by changing converter parameters, we hope that it should be possible to minimize the losses, and that will be done by simulation by Siemens. The other line we will look at is from Malmö to Simrishamn with a converter station in Ystad. And this is a single-track line with quite heavy suburban traffic. EMUs used on the line have quite high installed power, so we get very high power peaks. But these power peaks are just a couple of seconds long. And their idea is if it is possible to shift these power peaks, like just a few seconds earlier or later, we can maybe reduce the peaks by 30% or so without affecting the timetable. And then this way we are hoping that we can lower our investment costs. And also this will be done by simulation, and there we will see if it is possible to do that without affecting the trains.
Our task was to study the two cases. The first case regarding energy efficiency, with the task to reduce the losses by adapting the converter parameters. To be able to do this, we developed a converter model which has been used and in our simulation tool CityTrack, and also did an iterative process to optimize parameters with the tools which have been developed in MERLIN. So for the first study object with the reducing energy in the system looks quite convincing, so we optimize parameters but are still in the progress to find how much we could reduce the power, but it tends in the right direction that the energy in the system could be optimized by this method. For the second task, where we should look if we could reduce the power peaks of the system, we had two approaches. One approach was to modify, let's say, the train starts, the departure time of the trains, and the second was to alter the driving profile of the trains, taking into account not to shift the timetable. We already have preliminary results. Power peaks in the substation could be reduced by approximately 20%. The conclusion, both targets could be reached by optimizing the converter parameters. The energy flow in the system can be optimized, and also the energy demand could be reduced, so losses could be reduced. And the second subject looks very promising, and I think that it is demonstrated quite well that only short modifications in the timetable can reduce the power peaks, and then the goal of Trafikverket can be reached by that.
Hello. Yes, everything has more or less already been said, but so I will go a bit quick, at least this one. Quick to the descriptions of the line, because that will come again here, but I don't need to mention it again. The outline of the scenario, it was two different parts of it. One was strategic on the line Malmö-Alvesta, and the other was more operational on the line from Malmö to Simrishamn. One speciality with the rail power system we have in Sweden is that it is a 15 kilovolt 16.7 hertz system, actually the only one studied within MERLIN, and it differs quite a lot from a 25 kV 50 hertz system. Everything is fed either by rotating or static converters, and the whole network, in Sweden's case, more than 10,000 kilometers is interconnected without any phase separating sections or so. So you can have a power flow from the southernmost point of Sweden to the northernmost point of Sweden, more or less. Drawback is that static converters are more expensive than transformers, but an advantage is that you already have all power electronics installed in the network. So you actually have everything, not everything, but most of it you need for a smart grid, and you just need to control them in a more intelligent way in order to be able to, for example, save more energy or save investment costs. Even thinking of simulation, 15 kV 16.7 hertz network is more complicated to simulate. One aspect is that everything is interconnected, so you have to look at quite large areas. Another aspect is that you have to model the converters. And the converters are for sure more complex than a transformer because they are active components. The simulation has been done by Siemens with Siemens CityTrack multi-train simulation software. About the lines, I mentioned most of it in the video, but at least you see an overview here. Inside this black box there are the actual lines, and this map shows whole Sweden, so we are in the far south of the country. First strategic scenario on Malmö-Alvesta. 3 converter stations and a simplified traffic. What we did was to adjust the converter parameters in order to try to get the converters just to feed the railway which was nearest the converter, so that we don't transmit energy over a longer way over the catenary. There are a couple of different parameters you can adjust in a converter in order to achieve this. In this case, we worked with a no-load phase angle, no-load voltage, and amplitude control. That means you change or lower the voltage amplitude of the converter depending on the load and if it is reactive or active power. And what you do in practice is that you change the size of the area a certain converter is feeding, and in the optimum you more or less don't have any overlap. So your converter is feeding one circle and then you have the next one and it's feeding the next circle. Results from the strategic decision-making tool. All these parameters were altered from simulation to simulation. About 50 different simulations, I believe, we done. The worst one to the far left, what you actually see is that the converter in the middle, Hässleholm, takes the lowest load, and the both on the end take higher load. So you're transmitting lots of power over longer directions. Coming to the better solutions, the more optimal solutions, these one here are the parameters we are using today. You see quite clearly that all the converters share the load more or less equally. But the far left in this case is the best. Here, Hässleholm, the converter station in the middle, takes the greatest share of the load, which is quite logic when you just have a line with 3 stations, that the optimum would be that you have the most load in the middle and then less in the ends. And in this case, we weren't able to save so much energy, but it showed quite nicely that the idea of the strategic decision-making tool worked well. And I believe that you actually can save quite a lot of more energy when you optimize these parameters, but there's much more work behind in order to do that. The other part was the operational single-track line Malmö-Ystad. And Ystad is one of the converter stations in the Swedish network which has the highest difference between maximum load and medium load or average load. You see it in this diagram. The black line is the maximum load. The green line down here is the average or 50 percentile load. That means half the time the load is lower than 100 amps and half the time it's higher. And the maximum is 1000 to 1200 amps. What you see here is a whole year. So actually the average load is 1/10 of the maximum load. And the idea was, how can we lower these peaks here? Because they are expensive, because you need to dimension your converter for these highest peaks, but you have a very low utilization ratio. So the idea was to adjust the train runs within the timetable with help of the minute ahead optimization. One drawback here was that the minute ahead of optimization and the iteration then between them and the multi-train simulator had to be done manually, because this was just to check if the idea worked. So it was quite time consuming, and we didn't do so many iterations, but at least you can see that the peaks were lowered by 20–30%. So the blue one was the original traffic, the green one is the MIO optimization after 3 iterations. And there was no influence on punctuality, so timetable stayed the same. So we could show that the methodology of the MIO worked well, but we were still curious if there isn't more to do, because I believe that you could lower these power peaks much more than we achieved to show here. So we implemented in the simulation just a quick fix where a train which is on time gets its maximum power limited, and a delayed train can draw the amount of power it needs, and this is checked in every simulation step. So there's no prediction or so in it. It's just train early, limit the power. And what we were able to show with that is actually that you cut the power peaks by half or more than that. These short peaks here are due to iteration errors, because, as I said, this was just a quick fix and not meant to be some more permanent solution. But actually the difference here between 400 amps and 900 amps is one converter, and the price of one converter is a couple of million euros. So you can save quite a lot of investments in order to optimize this. Thank you.
Thanks very much, Niklas. You did a good job presenting the problem and the solution. I will now call to the floor the speakers of scenario 3. Yep, thank you. There we are. Reducing power peaks, consumption and costs in a suburban network. It's a scenario that is located in Spain. So we have 3 speakers. We have José Conrado Martinez, who is an industrial engineer specialized in electricity and mechanics and in railway technology from the Polytechnical University of Madrid. José Conrado has been working for ADIF since 1998. And he's now responsible for new technology projects and R&D projects there at ADIF. José is also a part-time professor at the ICA University. And within MERLIN, José was in charge of defining the needs of ADIF within the scenario 3. We also have a second gentleman here, whose name is Ramón Morales Arquero. Ramon is industrial engineer specialized in electricity. Sorry, I need to reread my notes. Ramon is an industrial engineer specialized in electricity, and he's also an expert in railways. Ramon has been over 14 years with Renfe, where he is head of assets management in the operation area of commercial services in Renfe Viajeros. Then we have Ruth Aregi, who is going to present the solution. Ruth is an engineer, and she has been working since 2010 as project manager for the Spanish rolling stock integrator CAF within its R&D department, where she is involved in carrying out energy-related simulations at train and network level. Ruth is MERLIN's deputy technical leader. She also contributes in architecture definition and is also work package 6 leader that involves simulations and also the Malaga demonstration. Maybe some of you have taken part in the workshop that we had in Malaga in October. Okay, so we'll launch the short video clip and then the floor is yours.
The Spanish scenario is formed by 2 different lines. First line, between Malaga and Fuengirola, is a 30 km length line with single and double track to suburban traffic. The line is fed by 3 electrical substations. The trains, type Civia is 464, circulate in a single composition with frequencies of 20 minutes. The first line has 18 stations along of 30 km, so trains must stop several times during the journey. As a result, two problems in normal at the grid's operation arise. On the one hand, a great possibility to recover braking energy. The problem is that many sections of the lines are single track and the frequency of train is low. The direct consequence of this is that the energy is not used and must be burned.
This line has both single and double tracks. Single tracks means complicated operation because all trains has to be synchronized. Being or not being synchronized has an important effect on the energy consumption.
Other common problems are the producer peaks of consumption during the starting of the degraded operation, that force to have some terms of contracted power very high and also at a high cost. Therefore, it is necessary to analyze the possibility of placing a storage system in order to reduce, even in degraded condition, those peak loads and also to know the most efficient use of the recovered energy. Other important issue to analyze is the possibility of minimizing the terms of contracted power to reduce cost. That means a direct saving in the energy bill.
MERLIN provides us two relevant tools to solve the issues and fulfill the needs of the suburban scenario of Malaga, namely a strategic decision-making tool and the REMES, the Railway Energy Management System. From the strategic point of view, it was determined that the deployment of energy storage systems could help to reduce the energy consumption, power peaks, and even the contracted power. The strategic decision-making tool was run to find the best combination of a number of design factors, like the energy storage capacity, its location, and the cost, to obtain the optimal results. From the operational point of view, the solution relies on the REMES. In other words, it relies on the deployment of the rail smart grid proposed by MERLIN. In this case, CAF, supported by ADIF, Renfe, and Saldo STS and the University of Aachen, implemented a real pilot case in the suburban network around the city of Malaga in Spain. Two of the REMES components were implemented and installed. First, the local optimization system, LOS, governing the area between Malaga and Fuengirola. And second, the Dynamic Onboard Energy Manager, DOEM, mounted on a Sevilla train, being both connected through the public 3G network. The test lasted for 2 weeks and proved the feasibility of the REMES concept and the MERLIN's reference architecture. The whole system saw its resilience to the degraded modes, changing the behavior of the agents to fulfill the timetable and the power contract. To sum up, MERLIN has provided a set of solutions for the suburban scenario in Malaga, thanks to its powerful tools, achieving better results than expected in both simulations and real tests.
Good morning. Good morning, everyone. On behalf of ADIF, I thank you for your attendance at this conference and on the Dutch final conference of the MERLIN project. And I want to also thank to UNIFI, UIC, and the Spanish Railway Foundation, the organization of this final conference in Madrid. Before that, my colleagues from CAF begin to explain in details the technical solution developed in this scenario. For my part, I shall briefly explain the implementation of the MERLIN project in ADIF lines. I think that this is an important aspect because there is a difference with respect to the alternate current lines. And in addition, my colleagues from Renfe and me, I will explain the difference of the general features of the selected line in this scenario and the different rolling stock that we use in the real test. Okay. If we develop a general comparison between the two types of systems, the alternate current and the DC current, I will focus on this general aspect. The first one is the typical application. The DC systems are usually used in operation in urban and metropolitan service and in main lines of moderate speeds. The altered current lines or the altered current systems are used also in main lines, and this system is always used in high-speed lines, as you know. Respect the electrical losses, is luckily by using a smaller voltage, electrical losses of DC systems are higher than in AC systems. Okay, the recovery of braking energy. This is an aspect. This aspect is having a great importance in recent years, mostly on DC lines. This is due to the use of this energy can have an important impact on saving energy of the line. As you know, in a DC lines, it is not used by other trains. This energy is dissipated in heat in the rheostatic brake of the trains. So the companies, the railway companies and the infrastructure managers are making a great effort to install the new technology for use this energy. For example, difference real is the difference power electronic equipment, the storage system, reversible substation, hybrid substation. And the last one is the electric power lines. Okay, DC railway lines are often connected to lines of low or medium voltage, is to say the distribution lines. These lines are usually submitted to higher disturbance respect to high voltage lines, especially with high density of traffic, so it is necessary a greater control. In summary, the objective of the infrastructure managers in this project is to act on these aspects so that will save energy and cost. But other objective very important is to improve the functioning of the electric railway system. For ADIF, the project MERLIN introduced two important advances to improve this aspect. On the one hand, the development of the RIAN systems, which is can optimize the power demand by each substation of the line. In the other hand, introduce the possibility of trains and different elements in ground can to interact in real time, so that it can modify the movement of the trains depending on the state of the different electrical parameters of the line. This will allow reduction of peaks and losses, optimize the recovery of braking energy, allow reversible substation or storage plants to recover that energy in a greater proportions, and better control on interaction with distribution network. Okay. The following map shows the ADIF DC network. Sorry. Sorry. This is the scenario number. This is the line for the simulation and the real test of the system. We select a line. This line in the south of Spain is a suburban line, specifically between the town of Malaga and Fuengirola. This line has a length of 30 kilometers with a maximum speed of 120 kilometers per hour, theoretical speed. The number of stops are 14, and we have 3 electrical substations for to feed the line. It's important to remark that the substation of the center of the line is a reversible substation. Okay, this is the first prototype of a reversible substation in a web network. This is one of the technical reasons that may select this line, because the idea was to have real evidence of the recovery energy. Okay, depending on the situation of the different elements of the system. In this way, energy stored in a storage plant could also be considered for the simulation and for the real test. Okay, Ramón.
Okay.
Sí, aquí.
Okay. I'm going to speak about the operational characteristic of C1 railway line. The most important characteristics are shown in this transparency. The operation is not very easy. It is operated in single and double track, and the traffic is very dense. There are more than 100 circulations per day. Now, I'm going to speak about the rolling stock that it's used in this railway line. This line is operated by Civia train. Civia train is a suburban electric train with a modular design. It can be configured with 2 or 3, 4 or 5 coaches. In this case, and during the test that we made in Malaga, we use a train with a configuration of 3 cars. The most important characteristics are shown in this transparency. This train uses 2 TCU converter with IGBT technology, and the configuration of 3 coaches use 4 asynchronous motor with a nominal power of 320 kilowatts. The most important is that this train uses the dynamic braking, and then the energy during the braking can flow from the train to the catenary. The most important mechanical characteristics are shown in the transparency. It is a light train. It's made with aluminium. And it uses a shared bogie between the both coach. Now, Ruth is going to explain us about and he's going to speak about the test that we made in Malaga.
Okay, the solution is divided in 2 big groups. The first are the simulations, and then the real demonstrator that was advanced by the video and by Isabel. So, from the simulations point of view, we have both the strategic and the operational approach described this morning by Roberto and Valeria. And the objective of the SDMT was to guide us and to optimize the cost. We were thinking on installing an energy storage system, and the open points were the number of energy storage systems, where the capacity, and finally the contractual agreement. So here we have the methodology we used. We analyzed the baseline simulations and real data collections. We detected some hot points, so we were able to define some location range and capacity length. We've had several configurations, and the strategic decision-making tool guide us to the optimum solution. We needed to have some iterative process, but we finally defined the strategic solution, which was the installation of an energy storage system near Victoria Kent station, which will allow us to reduce first the energy consumption, so the energy cost more or less in 13%, and then the power cost reduction was approximately 14%. The power was reduced by the energy storage system and also by adjusting the contracted power. So, assuming more or less that an energy storage system of this characteristic could cost 300,000 euros, more or less the payback could be 2 years. So it's demonstrated that the investment needs to be taken into account. Then, from the operational point of view, we decided to try to optimize the power demand at substation level. We used the REMS system, the MAO application, MAO minutes ahead optimization, in 2 slots. We defined the rush hours, from 7 to 7:15, and then from 7:15 to 7:30. We applied the flexibility to all the trains, so the instructions from ground were tried to fulfill by all the fleet. And here we can see, it's only an example, that at Los Prados substation we can reduce maximum power peak at substation level by 18%. The timetable of the trains were not changed because we were only changing the driving style.
I'm going to speak about the previous test that we made before the Malaga test. During the project, we made several measurements of energy consumption in the Civia trains that are operated in Malaga. Also, we made a test of resistance of the advance. The train that we used during the test in Malaga was moved from the north of Spain to Malaga. We used that train, number 199, because it was instrumented. It was ready to get the energy measure during the test. In this moment, from the north of Spain to the south of Spain, we made the resistance to the advance test in the Mancha region, in the middle of Spain, where the topography is flat. In Malaga, we made several tests from the end of September to the beginning of October, and now Ruth is going to speak about all the tests that we made.
So, from the previous testing, we had all the characterization of the train. So, okay, the simulations are always good, but it's paper numbers, but we were finding some tangible thing in order to prove the concept and the benefits. So, we set a loss in ground and the dome inside the train. This train is CAF's train, so it was easier, all the implementation and all the measurements, as Ramon said. And we have here both the loss and the dome. These are the main components of these projects. So we tested 4 different cases. The usual operation, where everything is working okay, the communication between all the components is working. Then we also tried to test a substation failure, how could affect to the REMs, a train engine failure, and finally a traffic congestion, which are really common in our daily basis. So, first, the substation failure. The Carvajal substation, and we simulated that it was working at half capacity. So the neighborhood substations were supposed to demand the needed extra energy. So at forecast level, and the DO requested some power profile, and the negotiation process between the loss and the train defined that it was necessary to change the profile. Changing a little bit the speed profile of the train, only at the accelerating part we can see that the power profile is also updated, and this could avoid peaks at substation level. The timetable is the same, the arrival time is the same, and the passenger doesn't know anything about it, but you can avoid peaks at power substation. Then, traction inverter failure. We can see that during our journey, we don't know why, but there is a failure, so the DOM it's able to detect that failure and is going to recalculate a new profile. So, which is the effect? That the power profile is updated, you need to reach higher speed in order to keep all the timetable and to reach on time to the station, but everything is okay. It's like you were not expecting anything. Then, finally, the traffic congestion. This morning, or before at least, Olivier told us about the problems at Macon substation. Here we tried to do more or less the same. We tried to simulate a stop between two stations, which was not detected first by the driver because he was not fitted with any DOM and any new technology, and then we simulated the same with the DOM. What's happening? If you have a DOM, from the traffic control center, you can have the information about this traffic light, so you can more or less update your profile. The blue line shows how the train needs to stop, which suffers from extra energy consumption because it needs to accelerate later. And the red line shows how at more or less 5,000 meters point and the new timetable was received, a new profile was generated by the DOM, and this allows to avoid the stopping part. More or less, it was detected that 15% of the energy could be saved between the blue and the red line attraction level. This was simulated in a scenario 1. This was also simulated in 3, but it was also proved by the demonstrator in a scenario 3. So that's all. Thank you very much.